We are in a different Kaggle competitions in top 25%, top 10%. We are doing a lot of research with the University of South California, especially it's focused on the medical data, and there's a lot of different implementation of neural networks that has been implemented. Some of them are the first implementation in the world in our GitHub. So you can definitely go and see them. Also, we were honored to be part of a deep learning book. So we made some suggestions there, and young fellow added some of our suggestions to the book. Yeah, and so this is our background. That's director of lab. He's connected via Hangouts from Yerevan. So, could you hear us? Yeah,
I can hear you. Do you hear my voice?
Yeah, awesome. We hear your voice great.
Okay, yeah. I hope that the deep learning algorithms that Google Hangouts uses to cancel noise will work and you'll be able to learn my voice throughout the whole presentation.
Yeah, so today we are going to go over 8 chapter of the book. It's really important part. It's one of the fundamental parts of deep learning. And so as Hrant is like main has a much more experience in in research than I. So he will be leading the presentation, and I'll be helping with the questions and answers. And I have also a lot of practical experience in deep learning. I'm co-founder of Teamable. That's the machine learning startup that uses deep learning and AI algorithms for the recruiting industry. So we're used by a lot of great companies here, including Twitter, including Stripe, including Lyft. So and so I have a lot of. I'm also leading the machine learning part there. So I'm also. So I have a lot of practical things there. Yeah. So let's start.
Okay. My name is Hrant, as Vazgen has kindly introduced. It's a great honor to have a conversation with you. I think that this format of reading a book and discussing it in an event like this is a very good format for learning something, and I think that's something that we need to also do in our media. So I will start from my presentation, which is tries to follow the structure of the 8th chapter of the Learning Book. If you have questions, please ask. I hope that I will be able to answer some of those. And if you have problems with hearing my voice, again, just ping me. We will try to figure out something. Okay, can we start?
Yep.
Yeah. Okay, thank you. So, the first subsection of the book is about comparing learning with optimization. So, optimization, as you probably know, is a large branch of mathematics which deals with minimizing and maximizing functions. So, if you have a function that is defined on some space and you want to find the minimum or maximum value of the function, then you have lots of tools that were developed during many decades by lots of mathematicians. So everyone in computer science, when dealing with a problem, tries to formulate his or her problem as an optimization problem in order to be able to use all of these tools that are developed by optimization community. So machine learning is not different, and the first thing that we want to do to learn something is to somehow formulate the learning problem as an optimization problem. So how do we do this? The idea is to define the so-called risk function. So suppose we have a data generating distribution. That's P data. And we know that this distribution generates pairs of X and Y, where X is our input and Y is our preferred output. For example, X can be an image, Y can be its label, whether there is a cat in the image or a dog in the image. And our goal is to find a function f of x that f of x equals to y for all the pairs x, y that come from the distribution. And the general strategy for machine learning is the following. We choose a set of parameterized functions. In our case, this is the set of neural networks. Okay, so when I say a parameterized function, I mean a function that depends not only on x, but also on some theta, which is, for different values of theta, we get different functions. And neural networks are good examples of such functions. Then we define a loss function, which we denote by capital L, and L measures the distance between f of x and theta and y. So basically, it measures the error that the function f has compared to the ground truth value y. And our goal is to find the best theta for which fx theta is very close to y for all the pairs. Okay, so that's the strategy. And we can formulate this as a classical optimization problem. We can define a risk function, which is denoted here by J star. And J star equals the expected value of the loss function taken over the whole data generating distribution. This is a very classical optimization problem that we would like to solve. Let's switch to the next slide. Okay, so there is one small issue here. The problem is that we do not know the data generating distribution. That's what we don't have as given to us. Instead of it, we have the so-called empirical distribution, which is basically given as a set of pairs x and y, which basically compose our training set. Okay, so we have a training set. It's a set of x and y pairs, and these pairs come from the original distribution, but we don't have the original distribution. We just have the samples. And what we have to do is to try to optimize the so-called empirical risk, which is the risk function of the empirical distribution, which is already discrete, and we can formulate it as a sum of loss functions over the whole training set divided by the number of elements in the training set. Okay, so this is the empirical risk. Now we want to optimize this empirical risk function, but it turns out that some functions are easier to optimize than others, and we know that there is a good class of functions that are called convex functions that are very easy to optimize. There are lots of algorithms to optimize them and to get exact solutions. But we also know that neural networks are not convex. So we have to use other algorithms that are not designed for convex functions. We know that there is a large class of optimization algorithms that depend on the gradients of f. And if our function f of x and theta is differentiable, then we may be able to use these algorithms. Many loss functions that come from real-world problems do not have useful derivatives. For example, the 0-1 loss function that is mentioned in many places in this book. It basically measures whether we have predicted the label correctly or not. Its derivative is either 0 or it doesn't even exist. So we can't use it in those gradient-based algorithms. What we do, we replace this 0,1 loss function with a so-called surrogate loss function, which has better derivatives. One example could be the negative log likelihood of the correct class. These functions are already differentiable, and they are very well suited for these optimization algorithms. We can still use the original loss function on the validation set. I think you may have discussed in the previous classes that you can split your data set into two parts. One of them is training set and the other is the validation set. You apply your training algorithm only on the training set, but then you evaluate the performance of your model on the validation set. And when evaluating the performance, you can use the original loss, not the surrogate loss, because you don't need derivatives there. And this is an important difference between pure optimization and learning. So in case of machine learning, you can optimize surrogate loss function, but evaluate your model on original loss function. And one more idea that we need to discuss is the concept of mini batches. Okay, so it turns out that many algorithms that work with gradients, they need to know the value of the risk function, empirical risk function, or the value of its gradient at every iteration. So these algorithms are iterative algorithms. They start from something and iteratively find better values for theta. And at each iteration, they need to know the value of the risk function or its gradient. And it's very efficient to compute this when the number of training sets, the training samples is large. Usually when we are dealing with deep learning, we want very large training sets. But for this particular problem, having a large set is kind of an issue. But fortunately, there is an easy solution to this. We can try to estimate the values of the function or the values of its gradient by computing these values only for a random subsample. We need to be careful when choosing this random subsample, but if we do this properly, we can estimate the values of the original function and the gradient with a very high accuracy. And this random subsample is called a mini batch. And the choice of the size of this mini batch is a very important problem in deep learning. I mean, in a practical problem. When you're training your algorithm on a limited hardware, you can't use very large mini batch sizes because it won't fit in the memory of your GPU. And you have to choose something that works for your problem well enough. It is important to see that the name of this random subsample is mini batch, but I think every deep learning framework that implements this call this parameter a batch size, not a mini batch size, which is kind of a confusion in the terms, but that's what is used in the frameworks. So if we try to summarize this subsection, we see the following picture. So we had an original risk function. We couldn't optimize it because we didn't know the original data generating distribution. We had to replace it with empirical distribution and got empirical risk function. Then we replaced the original loss function by the surrogate loss function, so it's easier to optimize it. And then we also require the concept of mini batches to make those computations practical on limited hardware. So basically, we did these three transformations from the original problem to make these learning problems tractable. And even after this, there are several challenges when optimizing neural networks. The first challenge that I want to discuss is the problem of local minima. So we know that when we are working with convex functions that have they have a single local minimum, which is also obviously global minimum, and there are algorithms that will easily find this minimum point. But neural networks have possibly infinitely many local minima, and gradient-based methods, we know that they tend to find local minima. So the question is, how should we guarantee that these gradient-based methods will not get stuck in this local minima and will not reach global minima? The interesting thing is that this problem is a huge problem in theory, but in practice it's not that important, because when you're dealing with real-world neural networks, it's a very uncommon scenario to get stuck in local minima. And why this happens? Please change the slide. This is an active area, basically, because there are many theories that try to explain this. Some of these theories, some very exotic branches of research, like statistical physics or random matrix theory or whatever, and they try to explain this interesting phenomenon. But it's still an open question. One possible reason that is easy to understand is that neural networks have lots of symmetries. Okay, so if you see this example, this is a simple neural network with a single hidden layer. This image is taken from Hugo Larochelle's videos. These videos are from 2013, but I believe these are still some of the best materials for studying deep learning. So here you can see, assume this is a neural network that is trained, and suppose the values of this weight correspond to global minimum. It's easy to see that we can change the order of the neurons in the hidden layer. We can just take a random permutation of these neurons, and we will get another set of weights that again correspond to the same global minimum. This means that even for this simplest case, the single hidden layer neural network, there are at least n factorial ways to permute the neurons, and it means that we have n factorial global minimum, at least. So this is one explanation why gradient-based methods actually manage to find global minima instead of getting stuck at local minima. Another challenge in neural network optimization is related to the so-called cliffs. In many scenarios, especially in recurrent networks, these loss functions have such areas that where the gradients are extremely large. These areas are called cliffs. So when somehow in the training procedure, your function gets close to this cliff, the gradients can get extremely large, and the gradient descent updates that about which we'll talk in a minute may catapult the parameters very far away. Actually, in Yerevan, we had many similar cases read last week, and later we discovered that we didn't apply this trick that is called gradient clipping, which kind of guarantees that the gradients should not be very large. And if we apply this gradient clipping, then this problem essentially disappears. So this is one of those challenges of neural network optimization that are solved more or less easily.
We have a question.
What kind of problem was this, like the image problem, text recurrence?
What kind of problem we were doing in year 1 and run?
What kind of problems? I think
It was RNets, right?
The exact problem. It was related to
RNets.
Okay, so we were trying to implement one of the papers that was published by Google researchers with the researchers from Tel Aviv University. It was about Stanford question answering dataset. Are you aware about this dataset?
Yeah.
It's a dataset of passages that are extracted from Wikipedia, and you have questions that are asked about this paragraph. And the problem is to find the answer in the paragraph. Okay, that's the challenge. And it's an open dataset, and it was released last year, I think, and there are many papers on that. And one of these papers was implemented by guys from Google. And actually, they did not release code, they just released the paper, and we tried to replicate their results. We have implemented their algorithm. I think we will release it very soon. I think some part of it is already released on our GitHub. You can check it out. And we can't yet reproduce their numbers, actually, their performance that they report in the paper. And one of the reasons was that when doing training, we had cases where training loss was jumping very far, like very high, and did not learn anymore. So one of the reasons was that we didn't apply gradient clipping on that.
How do you end up deciding that the gradient clipping was the problem?
How you ended up deciding that gradient clipping was the problem?
Actually, it's a pretty common problem. So we encountered it before. So there are more robust ways to determine this that we actually didn't do. But you can always print the maximum of the gradient, for example, over each patch. And you can somehow monitor this process, and whenever you see that this jump happens in the training process, and you can see in the logs that you have a very large gradient, it's very easy to catch these errors. This is some debugging technique that you can monitor your behavior of the gradient during the training. But actually, we didn't do this. We just came to the conclusion from experience.
So, any other questions? So let's continue.
Okay. The next problem is called vanishing or exploding gradients. So this is a very well studied problem. I think there are many papers that try to address this. And this usually happens in very deep networks and in recurrent networks. I will try to give the short idea of what's happening. So suppose you have a neuron in one of the top layers, and you compute the gradient with respect to its activation, and this gradient happens to be 0. And you know that neural networks are mostly made of multiplication operations. So all the neurons that are below this particular neuron, their gradients are computed by multiplying the gradient of the neuron above by some weights or some partial derivative of the activation function. But the main trick there is that you have multiplication operation everywhere. And when one of the gradients is 0 at the top of the neural network, then it propagates to the lower levels. And if you have too many zeros in the gradient, then your network doesn't even learn anything. So this is the vanishing gradient problem. The opposite of this is the exploding gradient, when you have several neurons that have very large gradients for some reason, and these large gradients are multiplied and end up with too large values. This is a huge problem, especially in recurrent networks. But this solution, this problem is mostly solved by many techniques. For example, back in 1994, Jürgen Schmidhuber and the operator suggested the idea of LSTM cells for recurrent networks. I think you will cover this in more detail in 2 weeks. Yeah, the 10th chapter of the book is about recurrent networks. For convolutional networks, which is the topic of the 9th chapter of the book, they suffer from the same problem, but there is a very good solution proposed by researchers from Microsoft Research Asia from 2015. This is called residual connections. Again, we will explore this topic. And very recently, just 1 month ago, the operators group published the preprint on arXiv, which suggested a novel way to deal with this problem. Essentially, they suggest to use a new type of activation function, which they call CELU, and they actually they provide a mathematical proof that if you use these activation functions, then you will not have vanishing or exploding gradient problem. And it's interesting that the proof of this result is written on 90 pages. So if you have seen recent papers on deep learning, you will never see a paper more than 10 or 15 pages. And this one is around 100 pages, 19 out of which is devoted to the proof of this statement. So essentially, this problem of vanishing or exploding gradients is solved in most of the cases. And now we can move to the actual algorithms that are used to optimize typical networks. We start from the very basic one, which is called stochastic gradient descent. I just copied the screenshot from the book to the slide. I think this is the best way to explain this algorithm. Essentially, you take a learning rate, which is denoted by epsilon, and then you take some initial values for the parameter theta. Then you check some stopping criterion, and while this criterion is not met, you do the following. You take a mini batch of m examples from the training set, and you compute the estimate of the gradient based on these m samples. Okay, so I hope you are familiar with this notation. So here L is the loss function. You take the sum over m samples of this loss function, then you take the gradient of this with respect to theta, and then you divide everything by m, and this is your gradient estimate. And then you apply update on your parameters. So basically you subtract from theta epsilon times gradient estimate. You use a minus here instead of plus because you want to find the minimum of the function, not the maximum, because the gradient points to the maximum of the function, and minus gradient goes towards the minimum, right? So the next slide has some visualization. This is taken from Stanford CS 231 and course, and I really recommend to watch this course. Videos are available on YouTube. This chart basically plots a function. Suppose you have a function that depends on just 2 parameters, and the colors indicate the loss. The red parts are the lower parts, and suppose your initial state is in this white circle. You compute the gradient. This gradient gives you some direction. It points to the lower parts, and then you just need to move along this direction. It's actually the negative direction of the gradient. Okay, so this is this arrow on this image is minus gradient. So you can see that this algorithm actually can raise several questions. If please change the slide. The questions are the following: how do you choose learning rate? How do you choose the initial value of the parameter? How do you choose the stopping criterion? And how do you choose the mini batch? We will talk about choosing learning rates in a moment. Initial parameter choice will be discussed in the next subsection. Regarding stopping criterion, I think we discussed this in these classes. The most popular and practical way to deal with it is to check performance on the validation set and train as long as the performance on the validation set is increasing. So whenever you see that more training does not improve your algorithms, your model's performance on validation set, you stop the process. I think that's the best criteria for stopping, although there are others. About sampling a mini batch, the most popular way to do this is to shuffle the training set, the whole training set, you shuffle it, and you choose the first M, then the next M samples, then the next M samples, and when you reach the end of the training set, when you reach the end of the epoch, you just reshuffle the training set and start from scratch. Okay, so now we move to the choice of learning rate. You can see on this image that if you have the direction that your gradient shows you, you need to decide the size of the step that you are going along this direction. Because if your size is too large, the size of the step is too large, you may jump over the minimum points, right? So you have to be careful here. This changes slide. Okay, so large learning rates can cause large oscillations of training loss. It's usually obvious when you plot your training loss during the training process and you see very large oscillations that you get some low values and then it jumps to very large values. It means that the learning rate is larger than needed. On the other end, smaller learning rate can cause very slow convergence. And if you see that you have started your training and you don't have large oscillations and your training loss is not decreasing fast enough, it usually means that the learning rate is too small. You need to increase it. So the general strategy is to start from a large learning rate and decrease the learning rate during training. This process is called annealing, and there are several strategies to do that. I think most of the deep learning frameworks actually support multiple such strategies. But this book prefers the first one, which is decrease the learning rate linearly for some number of iterations, and then keep it constant. But there are other ways to do that. For example, you can decrease the learning rate exponentially after m iteration, or you can decrease exponentially after some m iterations. And I would like to talk about one interesting thing here that I think it was last year or maybe 2 years ago. There was a paper by DeepMind researchers which suggested to use another neural network that predicts the learning rate to use in your original neural network. And this paper had a funny title, Learning to Learn by Gradient Descent by Gradient Descent. And the code is available. It's written in TensorFlow. And it's pretty interesting, and they actually demonstrate that for many problems, including image classification problems, their neural network find a better strategy for annealing the learning rate compared to other famous algorithms. Now let's talk about momentum. So one of the main problems of stochastic gradient descent is its speed. Sometimes it's possible to reach these minimal points faster. And one of the ideas to improve the speed is called momentum. basically, the idea is pretty simple. You introduce a new variable, let's call it velocity, and velocity is basically the average of past gradients. In fact, it's exponentially decaying moving average of past gradients. Okay, so you can see the formula. V is equal to some alpha times the previous value of V minus epsilon times the gradient. So epsilon times the gradient is the update that was used in stochastic gradient descent. Now we don't apply it directly on theta. We also add the previous values, the average of past gradients multiplied by some hyperparameter alpha. And yeah, it's important to note that we have added one new hyperparameter which we need to choose. I think that's it for momentum. The next slide shows an image which demonstrates what momentum does. So on the left side you see the optimization process or a simple stochastic gradient descent without momentum. Suppose you have a loss function which has a shape like this, which is a narrow valley. Okay, so you can imagine a narrow valley which is very long but very narrow, and you are on one side of the valley and you compute the gradient. The gradient points to the basically to the other side of the valley, and if you follow the gradient at each step, you will just jump between the walls of the valley, and you will do this many times before you reach the local minimum. But when you are using momentum, this velocity, this new variable, actually learns to accumulate the previous jumps that you did and kind of measures what you did before and tries to it basically adds more inertia to your process. So after a few steps, you can see that the gradient still points perpendicular to the valley, perpendicular to the walls of the valley, but the momentum forces the algorithm to reach the minimum point faster, because it has some sort of memory that during the past several iterations you have jumped towards the minimum. That's the main idea of momentum, and it's a pretty old idea actually. Another variant of momentum is called Nesterov momentum. This is inspired by Nestorov's work from 1980s. The difference is very small actually. The difference is only where we evaluate the gradient. Okay, so on the next slide you can see the image that basically demonstrates this. On the left side you see the normal momentum. You are in the point denoted by red circle, and you have two directions. One direction is given by your gradient at this red point, and the other comes from the memory, and the other comes from momentum. And you, what you do is you sum these vectors and do a step. But in case of Nesterov momentum, you do the step along the direction that is suggested by momentum, and only after doing this step you compute the gradient. So basically this gradient somehow tries to correct the direction of the momentum step by looking at the gradient on this new point. That's the only difference between the Nesterov momentum and the original momentum. Again, this image is taken from CS231N. The next thing I want to talk is about parameter initialization. So it turns out that optimization algorithms used in deep learning depend a lot on initialization. There is very little theory behind the commonly used strategies. Actually, there are some papers that suggest this or that strategy, but they usually provide some intuition, but they are not backed with strong mathematical proofs. One key idea that is pretty easy to understand and follow is that different neurons should be initialized with different weights. two neurons that have exactly the same weights at the beginning, then all the algorithms that we discussed today and all commonly used algorithms will update these neurons the same way. So you will always have two identical neurons, which is not a good idea because it's just a waste of resources. That's why it's a good idea to initialize the neurons with different values. Usually the biases are initialized as some constant values, but weights are initialized as random. Usually weights are sampled either from uniform distribution or Gaussian distribution, and there is not much difference between them. One of the most common strategies that was suggested by Nesterov and Benjo is one of the authors of the deep learning book, is if you have a layer which has n inputs and n outputs, then it's a good idea to take the weights of this layer from a uniform distribution between these two straight numbers. They provide some mathematical motivation on why they use these numbers, and actually these numbers work pretty well in practice. Another common strategy that is used especially, I think we have seen its effect on LSTM networks, is to use orthogonal matrices. So again, your weight matrices are random, but the rows are in some sense orthogonal. Okay, so the matrix is orthogonal. This somehow helps to make sure that your different neurons are pretty far from each other. And a couple of practical tips that maybe fall outside the deep learning book. In fact, if you are working on a practical problem, it's very common practice to take a trained network which was trained by some others and was tested in very large data sets, and just take the weights from this network. Suppose you are working on an image classification problem. There are many pre-trained networks available on the web that are already trained for image classification, and they are available for, I think, every major framework you might use. So in case of image classification, this might be VGGNet or ResNet. So you take all the parameters of these networks and initialize your network by these parameters, maybe except the top layer, because these networks are usually trained for the ImageNet classification task. I think most of you know about that. ImageNet is a very large data set of images, more than 1 million images, and they are classified into 10 classes. 1,000 classes. And these networks actually have 1,000 neurons at the topmost layer. So if your problem does not need 1,000 classes, you just throw the topmost layer and put a new layer with randomly initialized weights with the number of classes you need. But you keep the weight values for the other layers. And then you start to train this network. This process is usually called fine-tuning and works very well in practice. A few years ago, there was another type of pre-training that was popular, which was called unsupervised pre-training. Unsupervised pre-training is when you train a special sort of neural network or some other machine learning method on unlabeled data, and these algorithms sometimes manage to extract some good features from this data, and then you can use the weights of these networks to initialize a network for supervised learning. This was a pretty common practice 3 or 4 years ago, but recently these well-designed networks perform so well that there is no need to do unsupervised pre-training. if you watch videos or read papers from 3 or 4 years ago, then you will see that they are talking about RAS pre-training a lot, but I think it's getting less popular now.
Any question?
There's a question.
So with batch normalization, is rate initialization still a big issue?
Yeah, so you still can, you still need to use these types. Yeah, so basically it's still, it's not detailed.
Sorry,
So,
I think I didn't hear.
so the question was even with batch normalization, we still need these tricks. So you do still need these tricks.
Which trick actually, unsupervised or this?
In general.
In general,
So yeah.
Oh, yeah.
for example, I've seen.
Yeah, even with batch normalization. So, you know, if you have a well-trained network, and HGNet and ResNet are good examples for that, and you have a small training set for your own problem, then it's very easy to initialize your network with these parameters and then use your small training set to fine-tune. And I think in many cases it will perform better than if you start from scratch. Because basically, these networks were trained on very large data sets, and very often you don't have this much data for your practical task. I usually say that these networks have seen everything in their lives, so if you want to teach them something new, it should be easy for them. They have seen ImageNet. Did I answer the question?
Ravi. Thank you.
Yeah.
Okay. Okay, so the next thing we will discuss is adaptive learning rates. Okay, so I think a few years ago, researchers realized that it's very hard to find good hyperparameter values, especially the learning rates and the annealing strategy for the learning rates. And this kind of new types of algorithms emerged that try to somehow ease this problem. So what AdaGrad does? AdaGrad was probably the first example of such an algorithm. So suppose you have some global learning rate epsilon, again similar to stochastic gradient descent, and you have initial parameters theta. Now you add one more variable which is denoted by r, and you initialize it by 0. Again, you take the mini batch of n samples from the training set, compute the estimate of the gradient, and now, before updating your thetas, you accumulate the squared gradient. So R is equal to R plus G times G. And here this strength symbol denotes the element-wise multiplication. So it's important to see that R is has the same dimensions as theta. So for each of the parameters theta, you accumulate its squared gradient in this parameter. Also, it is important to note that R is always increasing because G times G is always positive, and you always add positive numbers to R, and it will always increase. And then when you have to compute update, you multiply a G not only by epsilon, but then you also divide it by the square root of your accumulated squared gradient. And you also add this small delta there. That's simply because of numerical stability. Because if R is 0, then you have 0 in the denominator, which is you want to avoid. So essentially, what this algorithm does is create a learning rate for every parameter. Okay, because every parameter will have its own coefficient that is determined not only by epsilon but also by r. And then its learning rate is always decreasing because r is always getting larger and larger. And when you divide epsilon by r, it's this coefficient is getting smaller and smaller. So your effective learning rate is always decreasing. And one of the main disadvantages of this algorithm is that this learning rate is decreasing sometimes too fast, like much faster than needed. And also it is important to see that those parameters that had large gradients, their learning rates are decreasing faster. So basically, if some parameters have changed a lot during the previous steps, now they change slower. So somehow this compensates for the difference between the changes of different parameters. That was adequate. The next iteration of this algorithm was RMS probe. So RMS probe was suggested by Jeffrey Hinton, and it's the same adagrad but with a single modification. So if you look how they accumulate the squared gradient, you can see that they have introduced one more hyperparameter, which is denoted by Greek letter rho. And this hyperparameter kind of controls the memory of the previous gradients. Okay, so it's again exponentially decaying moving average. So r is multiplied by a rho, so you kind of forget the old values somehow, and only then you add the square gradient. And the rest is the same. And this algorithm actually performs much better because sometimes learning rate can also increase if needed. And the last algorithm that I want to briefly discuss is Adam. Adam is probably the most popular thing now. It has a couple of more hyperparameters. And the main difference here is that they keep memory of both the gradient and the square gradient. The whole paper of Adam is written in the terms of probability theory and statistics. So they are talking about first moment estimate of gradient and second moment estimate of gradient. And they also bring some ideas from probability theory that these estimates are biased. So before applying the updates, they try to correct the bias in these moments. And only after that they apply the same update rule as we had in RMS probe. This is getting very popular. I think this paper was not even published in any conference or journal, but it's only on archive and it keeps getting lots of citations because everyone is trying to use that.
I have a question.
So the question is, all these algorithms, RMS probe, Adam, they use simple momentum, like in Adam. If we introduce Nesterov momentum with Adam, does it help?
So the question is,
Yeah.
the question is if we will instead of simple momentum use Nesterov momentum, will it Adam become better or not? Is there?
Yeah, this is an interesting question. Actually, my intuition is that there shouldn't be much difference, but I think you're free to test. I think I have seen this question in the meetup.com. So I have seen this blog post and where you tried to modify the other algorithm to use Nesterov like momentum. I didn't check the code actually, sorry for this. But the plots that I saw in this blog post were pretty interesting. So the general rule here is that if you are participating in a Kaggle contest, for example, then you're free to use any kind of techniques that you think they will help. And if you find better, if you get better performance on validation set and test set, then it's perfect. Like that's all what you need. On the other hand, if you are trying to contribute to the research, you will need to evaluate this idea on very diverse sets of problems. For example, if you check these papers where they introduce Adam or others, they try to cover many types of machine learning problems, or image classification or test classification, and they try to show that their method is universally better. So it's pretty hard to find an algorithm that is better than the others in many cases. I think with very few exceptions, including flash normalization, there are no such ideas. But I think it's a very good idea to test those ideas, to test those modifications. And if you manage to take some state-of-the-art architecture, state-of-the-art algorithm, and add this modification and get better results, that would be very important and interesting to everyone. Did I answer the question? I mean, I know I didn't answer the question exactly because I don't know how it will affect us.
Yeah. Continue. I also want to say that I have a friend that's doing his PhD related to the question you asked. So it's about changing and adding like different hyperparameters to Adam algorithm. So.
Yeah, I'd like to talk a little bit more about choosing the best algorithm, because this is maybe the most important problem when working in deep learning. So it seems really that Adam became the most popular choice recently, but it's important to understand that it's not the best in every scenario. Actually, I wrote in the previous slide, and I forgot to mention that one of the things that I have seen in many places related to Adam is that people tend to kind of say and convince that Adam is an algorithm for which you don't need to choose learning rate. Like regardless whatever learning rate you choose, it will adapt to your problem, and you essentially have one less hyperparameter. This is false, and it's important to not get into these traps, because in fact we had many cases where changing Adam, the learning rate of Adam even by 10 times caused significant problems. But I have to say that you can't compare it to HGD. For stochastic gradient descent, it's a nightmare to choose a good learning rate, but for Adam it's much easier. But again, you should not forget that it's still a problem there. Okay, so about choosing the best algorithm. I think the main practical tip, main practical advice that I can give is a quote from CS231, and they say that don't be a hero. So look at the papers, read the papers, and many researchers now report the hyperparameter values they use for their networks and just copy the algorithms and the hyperparameters. That's the easiest way to go with practice. And there is some real reason to do that, because in fact, the authors of these commonly cited papers actually have access to large number of computers, and they can do extensive hyperparameter search to obtain the best values for the hyperparameters. I gave screenshot from a paper about Inception version 4 architecture. That's a neural network architecture developed by Google Brain, and I think it's used in many Google products now. And in their paper, they claim that they got best results when using RMS prop algorithm with decay of 0.9, and they used learning rate of 0.045 and decayed every 2 epochs using an exponential rate of 0.94. I think there is no chance that a human without having access to a large set of computers can find these numbers. I think if Yaroslav is there, he can confirm.
No, he's not here,
But-
unfortunately.
Okay, so we will ask him next time. But my assumption is that these numbers were not obtained by educated guess. This was just a large-scale experiment on many computers, and these numbers performed the best. So it will be very hard to beat it. Actually, this was Google's submission to one of the contests, so
Yeah.
I'm sure they worked hard.
I have a question.
Yes. So the row 1, row 2, are they learned parameters for every every parameter? And how does it get updated?
How row 1 and
Yeah.
do you hear a question? So
Row 1 and row 2 of Adam.
yeah, how they are get updated?
Row 1 and row 2 are hyperparameters. They are not getting updated.
Okay.
They are the decay rates.
Okay. Thanks.
Of course, yeah. In fact, that's a very good question. If you look at the original definition of RMS prop algorithm, it says that global learning rate is fixed to epsilon. But you might see some papers that actually divide this epsilon by some number after, say, 2 epochs or whatever. I think I have seen a recent paper by Microsoft Research Asia that used Adam and not only used this row 1 and row 2 to decay the step size, but they also manually decreased the step size after some iterations. So still, you can take any of these hyperparameters and apply some annealing to that. Apply some transformations during the training process. Again, it's up to you, it's up to your patience and the hardware that you have access to. Okay, so the Learning Book has a large chapter about approximate second order methods. I'm not going to cover this in details. Actually, I don't even understand most of it. So we know that from theory of optimization, there are second order methods, so-called second order methods. They use the second order derivatives to estimate the shape of the function that you are going to optimize, and this helps solve many problems related to the choice of the step sizes. Sometimes when you have, for example, a convex function and you know the second order derivatives, you can directly jump into the minimum. And this is a very good feature for deep learning. But actually, very few people use it because these methods require a lot more computation. It's very heavy to compute the second order derivatives, the so-called Bayesian matrix. And I think they are very rarely used. I just recall one paper that where I saw this algorithm, one of these algorithms. It's actually a very famous one. I think all of you know about the style transfer problem. And the very first paper on style transfer actually used one of those second order methods. It's called limited memory BFGS. And I think the main implementation you'll find on GitHub by Justin Johnson. It's written in Torch, and it actually has the implementation of LBFGS. But I think it's very uncommon to use it, especially in production environments. And finally, I would like to talk a little bit about batch normalization. This is a new topic. I think many of you have heard about it. Again, I wouldn't get into the mathematical details. I will just explain what it is doing. So, suppose you have a batch of training samples, and you look at the activations of neurons for this batch. So if you fix a layer which has n neurons and you have m samples in your batch, you can get a matrix of activations for this batch, which is denoted here by age. Then you can compute the mean value for each neuron and the standard deviation of activations of each neuron. So the authors of this batch normalization paper suggest to subtract this mean from age and divide it by sigma, so that the activation, basically the distribution of activations of each neuron becomes something that has zero mean and unit variance. This helps a lot when training for several reasons. I think the book discusses one important aspect of that. The main idea is that when training a deep network, the neurons of one layer can actually influence a lot neurons on the other layer, and this influence can get very large when you are getting further away. So whenever, if you can guarantee that the activations of neurons do not depend on the other neurons, then this is a very good scenario for training, for the performance, for the speed of training. On the other hand, if you have an activation function like sigmoid, it's preferable to keep the data around zero, because if it gets too far to the right or too far to the left, you end up with a case where all your gradients are zero and basically your network does not learn. So this batch normalization solves several problems, and the trick is just to subtract the mean and divide by standard deviation for every neuron. But this trick has one disadvantage. When you assume that all your neurons have zero mean and unit variance, you are actually limiting the expressive power of your neural network. Because I think we have discussed this in previous lectures, previous meetups, that neural networks are universal approximators. So one can prove that neural network can approximate every continuous function with given accuracy. But if you apply this limitation, if you enforce every neuron to have zero mean and unit variance, this theorem does not hold, and you can't prove that it will express every function. So that's why basically if you do these shifts, you basically limit the expressive power of your network. So what the author suggested to do, they suggested to add new trainable parameters, gamma and beta. Gamma and beta are have different values for each of the neuron. And after doing this normalization, you kind of allow the network to scale back. So it can learn to scale back to its original distribution or some other distribution that does not have zero mean or unit variance. But the difference from simple neural network is that by default you enforce this zero mean unit variance, but you still give an opportunity to the network to choose a different distribution if it really needs that. So you don't limit its expressive power, essentially. So when you apply this trick, it turns out that training gets a lot faster. So we have seen cases in our lab that the training is getting twice faster, and it's not only faster, sometimes it also generalizes better, so the validation loss gets lower, which is also an active area of research that people try to explain why this happens. And one important trick that I want to share here that is sometimes ignored by many deep learning practitioners is that if you have a layer which has some nonlinear activation like sigmoid or whatever, you have to apply batch normalization before the nonlinear activation. So you need to scale your data to have zero mean and unit variance before passing it to the nonlinear activation function. This is pretty important for the performance of your network. So usually these deep learning frameworks like Keras or I don't know, Vazgen, they usually apply some nonlinearity by default on each layer. So when you need to use batch normalization, you have to explicitly disable nonlinearity and then add this nonlinearity after batch normalization. That's something that we didn't know when we were first working with this, and later it helped us to figure out what's wrong with our setup. I think that's it. Thank you very much for your patience.
Oh.
I hope this was. If you have questions, you can ask them now, and you can ask them later by this email. I will share the slides. Maybe it contains a couple of links that you might be interested in. So,
Actually, I wanted to
now
just
or later.
I want to thank you guys for being here. To your point about Yaroslav, he says he's watching us live.
Yeah.
That's what he just said. But thanks for the really, really cool slides. I think the slides are vastly improved on what's in the book and a really, really coherent presentation. And thank you for the contact information. I don't know if, Vazgen, if you want to share your contact in case people want to get in touch.
This is also, we have a, you can email me at Vazgen@teamable.com or Vazgen@yerevan.com.
Yep.
So also if, so I use a lot of this stuff in practical things, especially in image processing and in textual stuff. So if I can comment a bit about using this type of stuff in production. So basically, all the pro tips that Hrant mentioned are very, very important. So we never ever used any hyperparameters that were created by ourselves. We all used the things that were pre-trained. The other very important thing when you are doing this, when you are trying to, so when we want to solve some problem, is really, you really need to know the landscape of the, and we really, so Rat really did amazing work in presenting the latest results. So if you know Adam or you know what's the latest, you can for sure find the really relevant paper related to the things you are doing that is really relevant, and usually there's some intuition either in paper or in GitHub, and it's a really good idea to start implementing using that. So we gain a lot of even like competitive advantage in implementing some algorithms in using the latest stuff. In case of we really think that TensorFlow is top library for all this stuff. But if you are wanting to do research, Keras is much more better. But for production, and stability, the TensorFlow is the best. There are a lot of, especially in optimization things. So there's a lot of papers that are. So if you are doing NLP, there's a lot of stuff that is done for image processing. But if you know the basics, or you know, if you understand this, the gradient descent, all that stuff, you can use the techniques that is there and find relative information about NLP problems. So, for instance, so we have like that experience based in our experience. So we have like some stuff that some ideas in our algorithms that came from actually the other types of data, but it was applied to the. Yeah.
You talk about pre-trained models and using that. Have you tried using pre-trained models from ImageNet on something completely different, where it's not, maybe it's like microscope images or something like that?
We have experience of like we use some like weights from ImageNet on. So actually, Hrant can we have experience of like that wave recognition. Yeah.
Sorry, what recognition?
A wave recognition competition. So we were recognizing the spoken languages.
If you are getting into Kaggle, then that's the first baseline that you can put. You take a pre-trained model and you try to fine-tune it.
So what we have done, so the problem was to identify the spoken language in a WAV file. And what we have done, we have created the histograms of the waveforms, and then use ImageNet to classify them. And it was in one of the top solutions. So we also have like experience in initializing, getting some initialized value from ImageNet in some type of a network that was guessing the gender of in a picture. So yeah, so that was also worked really well.
If I can add something.
Yeah.
I think one of the most common cases of using pre-trained weight is word-to-vec or fast text vectors.
Yeah.
So in some sense, it's not a weight; it's a value. Right? If you want to use the precise terms, but again, when you all of these networks that work on question answering problems, for example, none of them start to learn the embedding of the words on their own. All of them start from word-to-vec or low or fast text. Because, like, again, these vectors were trained on huge amount of data, and they are readily available, and they were trained by the authors of the algorithms. For example, Richard Socher's team has trained low vectors, so it's hard to beat them. And yeah, then you can try to retrain, fine tune these vectors, which has some problems, and many people try to avoid that. But most of the state-of-the-art papers on question answering, you will see that, and those researchers that have access to large computers, like Microsoft Research Asia papers, they say that they just download low vectors from Stanford's website and use them.
For instance, one of this type of things we are doing in Tunable, we are using, for instance, to find differences between resumes. Yeah, and we use their like glove and fast text for trained vectors. So we can we have like a similar. So we actually have our own. We trained our own vectors, but I will fine-tune fast text, but we used fast text values at first, and we know like that like C++ and C is a similar vectors. In our data set, they are similar. And Python or Python and TensorFlow, they are close to machine learning and this type of stuff.
So previously we discussed about the gradient, like there is a cliff in the gradients. So like when you realized that this was the problem, like did you have to retrain the model from scratch where you began, or like you could do some trick to like just avoid it, take a step back and again start by clipping it?
I can grant you answer better. So
I couldn't hear the question.
so
Sorry.
when the question was when you realized that you have like that cliff issue gradient. Do you have to retrain the network from scratch, or do it, or be able to continue training from some network?
Yeah, I think you can train from close point if you didn't screw up before that. If you didn't have large gradients or the other problems before you actually discovered your bug, then you can easily continue. One problem here, which is maybe very technical, is that when you are using the networks with adaptive learning rates, they need to keep the information about these accumulated gradients. And if you are not, it's easy to forget that this information can get lost, especially if you are using lower libraries like Theano or whatever. You may forget to save this, and if you start to train the same Adam on a state where your weights are already trained for some time, but you have lost the accumulated gradients, then you might see some jumps in the training loss, because it starts from a very large learning rate again. So it basically forgot the accumulated gradients. You see a large jump, and then it adapts again and it gets lower. So this is pretty technical, but it happens if you are developing using lower level libraries.
I have another question. Like for the Adam optimizer, when we still have to choose the learning rate, right? So like we discussed like using another network to learn this learning rate. Can you do that with Adam, or like is there just a common
I haven't seen a paper that tries to learn a learning rate for Adam. But yeah, maybe that's something you can try. Although this network might learn to compensate for what Adam is already doing, because these networks are pretty powerful and they can essentially mimic what real Adam is doing, right? So maybe there is it's an overkill to use other network along with Adam. But I want to say that usually the default learning rate for Adam is 0.001, and in many cases it gives good results. But yeah, I will repeat myself. again, you need to be careful. Sometimes it doesn't work.
Yeah, makes sense. Thanks.
Question here. So the network which is learning the learning rate, how do we choose its learning rate?
Yeah.
Sorry, I couldn't hear.
So the network learns the learning rate. How we choose learning rate from that for it? Have you read?
Oh, I think it starts something random. Yeah, you choose something, but
I mean, it's also because they have.
I read it a long time ago, but there was a pretty interesting idea that during the training process, it actually was training two things in parallel. So one iteration, it was updating the weights of the original network, and on the other step, it was updating the weights of the network that produced the learning rate. And I can't remember exactly how they computed, how they defined loss functions. But yeah, this LSTM was learning to predict the learning rate for the prediction network. I think I can try to look it up now.
Did you use any non-standard loss functions? Like, there's some pretty popular classic ones, but is it worth using other types of loss functions or modified loss functions in practice or in production?
Well, yeah, that's a very good question. You know, it's a dangerous direction to go, like, especially if you have time constraints. For example, once we were trying to do some localization task, like you want to localize some object in an image, and this it looked natural for us to use regression, although we all know that classification works better for neural networks, and I think no one knows why. So we tried to use regression, and the results were terrible. And then we said, okay, we don't understand why, but let's switch to classification problem. So let's formulate our regression problem as a classification problem. So let's split your ranges of numbers, the range of numbers into small beans, and try to predict in which you fall. And this performed much better. I think we have attempted to use a custom loss function for one of the Kaggle contests, and we didn't manage to do that. But then I saw that other people of the same contest actually did that. I think it was a contest where you had to predict the retinopathy. So that's an eye disease, and you were given a large data set with labels. You had to predict the severity of the disease. And the metric that they used to evaluate your model was a very strange one. It was called quadratic log. Basically, you had 5 classes, but if, for example, if the correct answer is 0 and you predict 1, you are not penalized much. But if the correct class is 0 and you predict 5, you are penalized like 25 times more than if you predict 1. So the dependence is quadratic. So someone managed to apply those ideas in this loss function, and quite successfully. So it's possible, and you can experiment with that, but there can be surprises.
I have a question on batch normalization, and when you follow it with the ReLU, which is typically done, and in ReLU, if it's less than 0, the activation becomes 0. So does it present a problem that batch normalization are just centered to 0, and now half of your activations will be 0? And a follow-up to that is, how do you initialize the gamma and beta parameter for batch norm? Like, what values do you give for it to learn those parameters?
If I understood the question correctly, you asked how they initialize beta and gamma, these scaling parameters.
Yes.
As far as I remember, they initialize them to 0 and 1.
Okay. So,
But yeah, maybe it's better to double check because I'm not sure.
In my experience, so we never used anything not from the in a practical our problems. We never had any thing to use something, so any last functions or anything that we need to change.
My question is, what do you think of using a Bayesian approach in solving deep learning optimization problems compared to SGD?
Bayesian approach?
Yes.
Yeah, I think that's a very exciting direction, and I'm very happy that people who have a strong background in Bayesian statistics try to bring their ideas to deep learning. And actually, there are probably there are very good results already. So there was a paper that was explaining the effectiveness of dropouts using Bayesian concepts, and a side effect of this interpretation that they gave to dropout layer was that they managed to invent a variant of dropout that performs very well for recurrent networks. So dropouts for recurrent networks is a huge problem, especially if you want to apply a dropout on recurrent connections. I think you will cover this in a couple of weeks, but yeah, so there was a paper by Yoshua Benjo and his colleagues that if you want to apply dropout on a recurrent network, try to avoid applying on recurrent connections. Use them only on vertical connections. And this paper, which was based on these Bayesian concepts, they actually showed that if you apply dropout on recurrent connections, but you apply them exactly the same way on the whole sequence for the batch, it will still work. And it was obvious from their point of view, from their formulas, it was an obvious consequence. But other researchers that did not know about this didn't come up with this idea. So it's a very exciting branch, and I personally don't have much knowledge from this area, and I think that's one of the weaknesses that we need to solve. So we need to learn a lot about that because it provides new insights into the topic. Thank you for the question.
When you use one of the pre-trained networks and you just replace the last layer, do you find that just retraining the last layer is enough and leaving the pre-trained network, the other layers unchanged, or do you end up needing to, at some point after you trained it, having to modify the weights of the pre-trained layer as well?
Yeah, thank you for the question. That's a good question. So I think the baseline, the first strategy you do is to fix the other weight and just train the top layer. That's faster and that's more efficient. I think you can even save memory there. So that's your first approach always. And when you are not, the micro performance is not sufficient for you, and you see that you have training data that can be used to train more, then you can gradually make more layers trainable. Because if you have like 100 samples and you have 1 million parameters, it's actually very hard to train the whole network. Okay, this VGGNet and ResNet, they are huge networks. They have too many parameters, and if your training set is small, then you will probably damage something. So it's better to train less weights. But if your training set is large, then I think you can safely pre-train the whole thing.
Thank you.
So when you were stuck on the cliff in the optimization problem and you used gradient clipping to solve it, how did you realize that it was a cliff that you were stuck on and it was not a exploding gradient problem?
I think that exploding gradient and cliff are not mutually exclusive. So I think this cliff problem is some variant of exploding gradient, and the solution is generally the same. So gradient clipping helps a lot. So I wouldn't say that I'm sure that this was not a exploding gradient, this was a cliff. I think they do not exclude each other.
And another question, so when you're building custom architectures like 3D convolutional networks, and is there a standard data source that you could use for pre-training? Something that would help, something as standard as ImageNet Switch or something?
Sorry, I couldn't hear the question. You're asking for a data set for which kind of networks?
For 3D vision data.
Oh.
Is there something like
I can't answer this question. I've never worked with this kind of data.
Okay.
So we have to look it up.
Thank you.
Any more questions, guys? So no more questions. Thank you again. I just did a math in my mind, and I think it's maybe 3 a.m. in Yerevan right now. I think
morning. It's early morning. 7.
It's 7 a.m.
It's 7 a.m.
Early morning.
It's really early, so thank you so much for joining us for this whole thing. Guys, before we go, just a little bit of a house cleaning matters. So next week is CNNs with Louis Monier from Airbnb AI Lab. He's really cool. I'm really excited. He's a good presenter. And then we have Ian Goodfellow coming back for RNNs. And then Jeremy Howard is coming for methodology. And then Ian is wrapping it up, our last session for the applications. And then we'll have to discuss whether or not we'll continue for part 3 of the book. I feel like there is interest, so we might. I just don't know yet about the space and stuff.